Okay, so today I wanted to talk about some sort of logical preliminaries of topos theory. So but actually they can be viewed as general topological and not logical. If the idea of mathematical logic scares you, it scares me, then you can think of it as general topology instead. Okay, so what we're going to start with is that, propositional calculus deals with etc. some propositions and operations and or implication, negation, etc. All this can be interpreted in classical case as subsets of a certain set. Implication can be interpreted like this. Negation can be interpreted like this. And so this is an algebra of subsets in U. In other words, we just consider discrete topology on the set U, and we consider the set of open some subset of opens on this in this discrete topology. Thing is that and so P of U forms a Boolean algebra. We can replace now the classical logic with the intuitionistic one, and we will obtain another algebraic system called Hayton algebra. So the basic difference is that we pass from discrete topological spaces to continuous topological spaces. And so Hayton algebra has the same operations and or negation, implication, etc. But models for Hayton algebras are not necessarily discrete topological spaces, or in even more highbrow terms, we can consider local. Yeah, so it's written like this. I'm not sure how to say it, but in French, I think it's local, local. And so those form the model for Hayton algebras. So we consider opens on topological space or on a local, and then this thing here forms a model of Hayton algebra. However, we have to reinterpret certain operations. So implication now becomes the following. So UV is U implies V is the largest subset. Sorry, not a subset. It's just the largest open set W such that this intersection belongs to V. And negation so is to preserve open subsets needs to be defined like this. So a negated open subset is the interior of set theoretic complement if we are working with topological spaces, or it is or it can be defined like this, and sometimes, well, sometimes it is not exactly negation, but at least this definition works not only for topological spaces, but for arbitrary substitutes of topological spaces. Okay, so that's the idea behind creating algebras. So we just go from classical logic to intuitionistic logic, and we obtain this new definition. But I can now I want to give a rigorous definition of Heyten algebra. So this was very hand wavy. Now I will start from the very beginning. So I will start from the concept of lattice. So lattice is a Poe set such that as a category it has all products, well, all binary products and coproducts. So yeah, if X, Y, and Z belong to L, then X less or equal to Y is equivalent to existence of unique arrow from X to Y. So coproduct, yeah, so that's just how we restore the pole set structure from categorical structure and vice versa. That's very common. And so a coproduct is denoted by supremum of two elements, or sometimes it's denoted like this, and infimum of two elements is sometimes denoted like this. If we have 0 and 1 in our lattice, then we have the following inequality for each element of the lattice. And so 0 and 1 are respectively respectively so sorry, irrespectively terminal sorry, I'm a bit brain dead. Here. Effectively initial and terminal. Objects in okay. So a Poe set can be given explicitly as a set with operations. So we have equations like this. And one distributivity law. Well, sort of distributivity. Well, the relationship between two operators in mix. And so these equations give so These conditions give us equations on two operations. Two operations and two unary operations. So these equations can be used to define a pole set object in an arbitrary category, which can be useful. And so the pole set structure in this case can be restored using the following equivalences. So have this allows to restore the pole set structure. Okay. So this was a general definition of a lattice. Now I move to a more specific definition of distributive lattice. I don't think that I need to give any examples here, but if one wants, one may consider subsets of a given set. There, it is clear how to interpret all these operations. Okay. Distributive lattice. Yeah. Lattice. That we have the following distributivity law. So the condition that a pole set is distributive with respect to arbitrary unions, or with respect to this operation taken over arbitrary index set, means that distributive lattice with distributivity over arbitrary set or union is called frame. And so frame is basically a dual category of open subsets of a topological space. And so the formal duals of frames are precisely local. And so that's the definition of the object which I was referring to at the beginning of the talk. So frames and their pole set morphisms form a category frame, and its opposite is called category of local. I don't know how to denote it. Let's denote it like this. And so we just extract the information we need from topological spaces, that is the structure of a system of open subsets, and it turns out that we only need distributivity with respect to arbitrary unions from this. And so this is sufficient to do general topology. But I will not dive too deep into this pointless approach to topology, like not pointless, point-free approach to topology. Okay, so let me get back on track. Definition. Complement. Now, lattice. The element X in the lattice L with 0 and 1 is also in the lattice such that intersection with X is 0 and its union with X is 1. So let me remark that distributive lattice complement unique. Note that the existence of the complement is not necessarily true. For example, we can take an arbitrary topological space, take there an open subset which is dense in X. For example, I don't know, something with Zariski topology and some complement of 4-dimension 1 subvariety. Then the complement of X, if it existed, should be the interior of X without U, which is an empty set, obviously, because of the density condition. But the complement, but the condition that U together with an empty set is equal to X is not satisfied. So, well, we don't have a complement in this sense. So that is why this thing is often so this thing here would be, of course, will of course coincide with this open subset, but since we don't have this defining equations for the complement, it is the reason why this open subset defined like this, or in any lattice, anything defined by this equation, is often called a pseudo complement of so if a complement existed, it would be given by such a formula, but in this case, the complement does not exist, and this element does not satisfy, for example, this equation. Okay. So let me briefly mention an important theorem due to Stowe for any Boolean algebra. There is U such that A is isomorphic to the Boolean algebra of subsets of set U. Okay. So this is sort of a realization result. We can say that each Boolean algebra can be realized as an algebra of open subsets of a discrete topological space, this topological space being precisely U. Okay. Now to Hayton algebras themselves. So Hayton algebra or Brouwer and lattice is a full set with finite order quantities. That is partition closed. That is where each object, each pair of objects has an exponential object. So, in other words, each algebra zero, 1, and for each. So it is obviously a lattice. The Hayton algebra, if there is if it's a lattice, there is 0 and 1, and for any two objects we have y to the power of x, which is usually denoted like this. By definition of exponential object, we have an adjunction which looks like this. So, yeah. In other words, x to y is the least upper bound for all z such that x is less or equal to y. In particular, y is less or equal to. Using Hasse diagrams, this can be represented like this. Here we have the meet of these two elements. Here we have this exponential object. And so we have this inequality, but also we have a condition that intersection of these two objects should be equal to the meet of x and y. let me give you an example of this exponential object in practice. We will once more refer to category of opens in topological space. So H is the category of opens in topological space. So the empty set is obviously 0. The whole space is obviously 1. Union and intersection and or are interpreted as intersection and union. And the exponential object is computed like this. It is a union of all W such that the intersection of W and X is a subset of Y. So using distributivity, we can see that we have all. So we see that the union of all W such that intersection is contained in V is in fact this. Okay, in a similar way as we did with the lattice of opens in topological space, we can show that any by complete lattice distributivity property is a Hayton algebra. So any Boolean algebra is a Hayton algebra, but the converse is not true for obvious reasons, because, well, Boolean algebra represent something which is like a topology on a discrete set, which is like a discrete topology, and Hayton algebra represent various topologies which are not discrete. So yeah. Now I want to show how Hayton algebra sort of interpret the usual identities from category theory in terms of logical operations. This, to me, it was quite illuminating that all identities from mathematical logic can be, not all, but many of them can be obtained as a result of general categorical identities. So in the closed category, we have canonical morphism from x to x times y to the power of y. So it's co-evaluation, and we also have an evaluation morphism, which looks like this. In Hayton algebra, we have the very same thing. So the morphism becomes the inequality sign, and the exponential becomes an implication. So we obtain something like this. Similarly, in the opposite direction, we have this identity. And now we can interpret the next series of the identities. So we have an obvious identity. 1 to the power of x is 1. X to the power of 1 is x. And in Heyting algebras, this just becomes two identities of the following form. Now note the fact that since we have an adjunction between taking exponents and taking products, it is a right adjoint of the product functor. It preserves products. So preserves limits, products in particular. So we obtain the following identity, which is, at least for me, it is non-trivial to understand why it works. I mean, you can obviously write down some sort of true-false table, but in arbitrary lattice, it is not clear how to proceed with that. However, here we immediately get the following result. Similarly, one can write down the associativity condition for taking exponentials. So we have an isomorphism. Yeah. And we may write it down in Heyting algebra like this. And obviously, we can use the fact that the product is now left adjoint. To obtain the following. So we have an adjunction, and so it preserves all products. In particular, we have distributivity. So that's a property of Heyting algebra, which follows from existence of exponentials. When algebra is always distributed. We also can write down the condition that the multiplication is commutative and use the adjunction to form several other identities. So okay. So another thing we can use this implication for is the following. So this is a function which is called countervariant in the first variable, called the only variable. And so we can use it as a functor from H to H opposite, applied from the right, and as a functor from H opposite to H applied from the left. So these equivalences are adjoined to each other. Well, they're adjoined to each other, and since left adjoints preserve coproducts, coproducts become products under the action of this implication operation. And so we have the following identities which follow from adjointness. So the coproduct became product. Sorry. Okay. So now I want to demonstrate one of the reasons why we're interested in Heyting algebras. So I already said that they sort of model topological spaces, but another reason is that basically for any pre-shift category, the subobject lattice of an object forms a Heyting algebra. So consider category that's the opposite for category C. Bring P in this pre-shift category, whole set of subobjects. I actually don't think that we need smallness of C. We only need the fact that, well, the category of pre-shifts is well powered. So this pole set is a Heyting algebra. Okay, so I think that we can make a break here, and I will start the next part of the talk from proving this proposition. And then we will talk about quantifiers as adjoints. Let's reconvene in 5 minutes. So what we wanted to do is to prove the following proposition, that we have a pre-shift category for some small category C, and we have a pre-shift, and the pole set of subobjects forms a Heyting algebra. To do this, we need to give operations on this Heyting algebra, this potential Heyting algebra. And so to do this, we just consider pointwise operations. So given S and T subobjects of P, we define SMT C conjunction of disjunction of SMT as a union. When analogously, a conjunction is defined as an intersection. This makes sense because S and T are so S and T are subfunctors of P, and therefore SC and TC are subfunctors of P of C. Therefore, it makes sense to take their intersection and so on. Yeah. So to define implication, we need slightly more involved construction. The value of implication on an object C is instead of f P of C such that for any function from C to C, in C, so this is just the pullback element of X. So it belongs to S means that XF belongs to T. So this is very much the same as the definition that it consists of all such subsets such that the intersection is still a subset in well, in this I'm not sure how to say it, in this implicant of the implication. So and to define negation in this context, yeah, so why we didn't define this implication in more in sort of easier terms point-wise is because under such definition, it does not form a subfunctor, and we want to get a subfunctor from doing operations on subfunctors. So that's the reason that we needed this involved definition here. So the one is obviously P itself, as 0 is the constant empty set functor, which takes the value of empty set on each subfunctor of P. And negation is defined like this. It is clear from this definition that in general we don't have an equivalence that negation of S and S together give us the whole P. Okay, so now it is really straightforward to verify that with such operations we indeed get Heyting algebra. So yeah, the principal difficulty here was to define these operations. Now it is more or less clear how to proceed from here. Okay, so I think that is more or less it for Haitian algebras. It was sort of short excursion into the concept. I don't think that it was sort of a nice demonstration of how logic can be interpreted in terms of category theory. And I want to continue on this path by considering quantifiers in terms of category theory. But I don't think that we will really need work with the concept of Haitian algebra, that we'll need to work with the concept of Haitian algebra for a long time. So yeah, that was sort of an excursion. Now on to quantifiers. This is another semi-topological or logical story. But mostly it demonstrates that actually most of classical logic can be formulated in terms of category theory. So the goal here is to describe quantifiers for all and there exists in terms of functors. And we can do that. First of all, we start by considering the terms of this form, where S is a predicate of some form. And it can be interpreted as a subset in X times Y, where defined by pairs X and Y, such that S of X and Y is true. Then for any S, for any X S X Y describes a related subset T in Y, consisting of Y small, such that for any X, the pair X Y belongs to S. So basically, we have a projection from X times Y to Y, just the usual projection of a product to one of its factors. And we now can define the following sets. So for any sub P S, it's just a set T, which consists of which looks like this. So it is just the set T that we defined above. And at this sub P S is analogously defined set subset of Y's such that the following holds. And so we have two categories, which are, well, we have two lattices which can be regarded as categories. Boolean of X times Y and Boolean of X, or Boolean of Y for that matter. And we get a pair of functors from P of X times Y to P of Y, which are just for any sub P and exist sub P. So let me state the theorem. For projection from x times y to y, functors this p and for any p form are left and right joined pre-image functor yeah. So proof of this theorem is very straightforward. For s in x times y and t in y, we have the following equivalences. So p star of t is a subset in S if and only if t is a subset in the projection of, well, in this thing here. And this is just from the definition of for any sub p of S. And also we have that S is a subset in the pre-image if this projection is subset in T. So this thing here is just a projection under P of S. So this equivalence is also very clear. Now it is only a matter of interpretation to see that the condition that we have inclusions in Boolean posets is equivalent to the condition that there is, and there is also only one always. If there is a morphism, there is only one morphism in this home set. And on the other side, we have the appropriate home set where the functor p star is replaced by the functor for any sub p on the other side. And so we get the natural equivalence between two home sets. And similarly for exists sub p and p star. The same, of course, can be done for another function, not necessarily p. So let me state the theorem. For any f from z to y, f star from py to pz, is left. So this is of course sets as left and right joins for in sub f, which are defined in the following manner. So this is just an image under F. So it consists of Y such that there exists Z in S, such that Fz is equal to Y. So this is just an image of S under F. And for any sub F is defined similarly to for any sub E. Yeah, so the proof is verbatim the same as for this theorem. We also write down similar equalities. We just replace P by F, and we get the desired adjunction. Okay. So what we've got is the following diagram. So if we have function z of f from pz, so from z to y, then we have a pullback on which goes in the opposite direction on Boolean lattices, and we have adjoints look like this. In more general terms, this construction can be applied to arbitrary sets over another set. So this becomes a base change morphism. We can consider f star, which goes from set over y to set over z. So the value of f on an element of this slice category is just the following fiber product. So we had f from z to y, and we just pull back this object to get another object. And also this can be viewed as changing the index procedure. So we have a family of fibers sort of here over y, and this can be viewed as changing the index of these fibers. So we obtain the family indexed by elements of Z. So the following theorem holds. For any function from Z to Y between two sets, the pullback functor from set over Y to set over Z as left and right. This theorem is actually a manifestation of a more general result, which I will now state, which says basically the same, but for arbitrary categories. So So let C be category pullbacks. Let B be an object in C, and consider a morphism from B prime to B. We have then a base change functor from C over B to C over B prime. It has a left adjoint and if C over B Cartesian closed, then it has a right adjoint. So the left adjoint is just a composition with F. Okay, so yeah. So this is the most general form of this theorem about quantifiers that we can state. We actually can deduce from it the following proposition. So if we have two objects in a complete category C, such that B over B is C over B prime are Cartesian closed, then pull back on the arrow F from B prime to B preserves all the limits C over. Yeah, so this is obviously deduced by observing that we have the right adjoint in the case of Cartesian closed category, Cartesian closed category C over B. So this adjointness then implies preservation of colimits. So now let's try to prove this theorem, this general statement about categories with pullbacks and base change morphisms. So let's start from the following case. So assume that B is equal to the terminal object. Terminal object. C. So C over 1, just C itself. And the pullback along so we have a unique arrow from B prime to 1, and the pullback along this arrow is just a functor which takes product with B prime. So the morphism from any object A times B prime to B prime is obvious. It's just a projection on the second factor. And so assume that we're given any object H from Y to B prime. And C over B prime. Then an arrow from such object to this product object is just an arrow from Y to A. Thus, an adjoint of this functor, which takes the product with B prime, is just a forgetful functor, which goes from C over B prime to C. So yeah, and so it is given on objects by Y to B prime and returned in Y. And on the other hand, an arrow from A times B prime to B prime to another object Y to B prime is just an arrow T from X times B prime to Y. From A times B prime to Y. And C such that we have a functional equality that this thing here is equal to H. So that's just the condition of the triangle. Now we may apply the exponential adjunction to see that that this arrow T corresponds under exponential adjunction to T prime from A to Y to the power B prime, such that H to the power B prime composite to T prime is the composite X to 1 to B prime to the power of B prime. So here J appears as a coevaluation from B prime to B prime. So the arrow T prime in turn corresponds to under pullbacks to T prime of T2 primes from X to, sorry, from E to gamma H, where gamma H is the pullback of the following form. Thus, gamma H, which is a pullback of this exponential along this coevaluation map J, is the right adjoint. Is the right adjoint of this product function. In general case, we can reduce ourselves to this absolute case where we have B as a terminal object. So assume that we have now an arbitrary arrow from B prime to B. F is an object in the slice category C over B. And an object over F is just the following commutative square. So now we just need to note that this square is completely determined by the map from X to prime. And so this is obviously an object of C over B prime. And so we have an isomorphism of slice categories. So C over B prime over C over B over F is the same as C over B prime. And the pullback along F from C over B to C over B prime is then, which by the previous observation is just the same as taking two-fold slice category, is reduced to the previous case because F now is the terminal object. Okay, so I think this completes the proof of this theorem. And also, I think that ends my today's talk. Are there any questions?
I have a question.
Yes.
What are the sources for today's lecture?
Oh, okay. So the sources, as usual, for today's talk, for basically any talk on topoi is Moirtake, MacLean, sheaves, in geometry and logic. And for today's talk specifically, it was chapter 1, sections 8, 9, 7, 8, 9.
Thank you. I'll check that.
Okay. Thank you for the question. Are there any further questions? If no, thank you for coming. I'll see you on Friday, when we will finish speaking about monoidal model category.